So I will present some research things that we are doing in the Quantic research team, okay? So first I will motivate the title, Quantum Error Correction and Feedback, by this. So everybody knows what is a feedback scheme, okay? It is essentially to counteract perturbation W, or to have a precise, here it is a regulation goal. And typically, when you look at what is quantum error correction, initially what was performed by Shor in the late 90s, it was a feedback loop, in fact. So you want to store information, what is, I will say, quantum information into your system. So it is typically quantum information. You can see it as a vector. A qubit is a vector of dimension 2 of unit norm. Okay, it is this. So any vector of dimension 2 of unit norm, but with complex coefficient. Okay. So this is your quantum things, and you want to encode it to support it in a physical system. If you do this up to now, you see in current experiment for elementary manipulation of this qubit, it was the error rate is 10 power minus 3. In our machine, in our classical bits, the error rate is 10 power minus, I will say, 19. Okay? So it's not the same rate. You have almost no error in our machine, in our classical machine. Here, of course, because of this error rate, we need, in fact, to encode a logical qubit, okay, in several physical qubits. But in this case, the overhead, as it was computed, it is in this reference, it was typically 1,000 physical qubits to encode a logical qubit. So it is clear that the building block of physical qubit, you should, in fact, increase its performance, okay? And in this increase in this performance, it is clear that for that, in fact, you can use, when you want to stabilize your system with respect to perturbation, here perturbation is noise, okay? Then you need feedback loop. And typically feedback loop, it can have two kinds of feedback for quantum system. Either your controller is, as in the above picture, a classical system. So you have your system in the quantum world. You have parameter, your control input, in fact, that you manipulate. Okay? It is classical signal that you inject in your system. And you measure something, of course, it is quantum measurement, but the measurement outcome is also a classical signal. And you close the loop. Okay? It's typically what's going on, in fact, when you initially for quantum error correction. It is something like this. Okay? But, in fact, you can also imagine that, in fact, your controller is also a quantum system. Okay? And it is called in physics autonomous quantum error correction. The autonomous is important. Okay? And in general, so I will focus here my presentation on, in fact, on typically quantum controller and what we are doing in the group to develop typically quantum controller such that the physical qubit, okay, had better, in fact, quality, better coherence, better lifetime, and so on. Okay, I will discuss this in my presentation. The last point, you should be aware of the fact that this way of looking at, you know that Schrödinger evolution, okay, it is something like this. So here is the outline of my talk. So I will describe, of course, what are first the model behind this system. Okay, what are the models? It is important to have a structure of a model, okay, on this. And you will see in there that the coherence can be seen as dissipation, quantum dissipation, okay. And we want to engineer, in fact, quantum dissipation such that you converge to something that interests you. So it is what is called also dissipation engineering or reservoir engineering, okay, quantum reservoir engineering. And the idea goes back, in fact, to what is called the optical pumping of Alfred Kastler. It was in the middle of a previous century in Paris, okay, this thing. Okay. So let's focus on how to consider this. But first, I will describe, of course, at the end, you should always be aware that at the end, you are in the lab with experimentalists. They have classical input signal, classical output signal. At the end, it's the way that you are looking at the system. So I will first describe what are the models here where, in fact, you can inject, add to this scheme some classical input and also quantum measurement, okay? But I want to see what are the models that you can use here, what are based. So you see the dynamical models. I will explain their structure. It is important. Then I will explain a little bit what is, in fact, dissipation engineering, and we will make a sort of, it is an analogy with a watt regulator. Okay, it is exactly the same thing, but where, in fact, a quantum system controls another quantum system, or where, for a watt regulator, a mechanical system controls another mechanical system. Okay? And then I will discuss something that we are looking in the group, which corresponds, in fact, what is called CAD qubit and grid qubit, GKP qubit. I will detail a little bit what we are doing on this. Okay. So the modeling rules. The modeling rules are always the same. You have first the Schrödinger evolution, deterministic one, okay, where, in fact, you use the wave function, psi, ket psi, it is a vector, or also you can use this guy, which is the projector on the direction of psi, which is called the density operator. So if you write this equation for rho, you obtain here the commutator with what is called the Hamiltonian, and in the Hamiltonian, in general, you have your control signal input, okay, appearing. It's a function of time. Then the second point here, it is typically something which is completely quantum. It is what is called the measurement, the collapse of a wave packet. So you assume that your measurement is attached to an operator O, which is Hermitian. You consider its spectral decomposition. So you have eigenspace, okay? The orthogonal projector on each eigenspace is labeled by Y. Y will be the information that you get from the measurement, okay? So Y label the orthogonal eigenspace of your system. And the rule of the game is this one. If you measure O, you assume that it is instantaneous. You have the orthogonal projector of psi on this eigenspace, which is labeled by the measurement outcome, okay? And the way you get information from your system is by this statistic. The probability to detect, in fact, mu, okay, here, is given, here, you see, when y is equal to mu, is given by, in fact, this quantity. And of course, since you want to keep, in fact, the length of the wave function by 1, you have to renormalize. And it is this renormalization that gives you the probability. This is basic rule of quantum mechanics. And so this is completely specific to a quantum system, okay? And the last point, which is also completely specific, is that, in general, you never measure your system directly. You couple it to another system, which is called the matter, okay? Your measure system interact with your system through, typically, in fact, Hamiltonian evolution here. So here, and you have to deal for composite system to tensor product. We change completely the rule of the game as with respect to classical system. Classical system, it is Cartesian product. The dimension adds. Here, the dimension multiply, in this case. Okay, and when you see here, you have tensor product. So you see, just to explain a little bit this thing, so you have the Hamiltonian of a system alone. So it is identity on the matter. So you have your system with this Hamiltonian, the matter with this Hamiltonian, and you have typically the interaction between the two, which is a sum of tensor product of operator on your system and operator of the matter. Okay, it's the way. So you play Lego with this. Okay, I give you the rule how to connect the blocks and how to define things. Okay, this is standard quantum mechanics. And this is the first thing. So this is the basic rule. And if you want to understand a little bit what's going on experiment, you need, in fact, to master, in a certain sense, 2 elementary quantum systems. you have a simplest quantum system, which is a two-level system, okay? It is this one, it is a qubit. And here, all what you have, it is with, in fact, Dirac notation. Here, this is the complex, in fact, plane, C2. Here, it is the density operator. It is something like this, okay? It is a Hermitian matrix, 2 by 2, with complex entries. And here you have an operator, which is sigma minus C. Sigma minus, it's get from the excited state to the ground state. It is the way that you can interpret it. Typically, if you apply sigma minus to E, you go to G, okay? Because you applied here, just here. You go from E to G, and if you apply sigma minus to G, you obtain 0, nothing. So it is the disexcitation. And the Hermitian conjugate is the excitation, and so on. And with this operator, you, in fact, you obtain all the, what is called the Pauli operator, all this thing. So you have, it is always operator, but do not commute, and you have the commutation rules, and so on. Okay. And typically, your system has a certain energy, G, ground state, excited state, and with your, in fact, control output, input, okay, you can sigma x, you see sigma x, it is something that, in fact, exchange E and G. It's a swap, okay? And so you can, in fact, drive your system between E and G with this, okay? Just to be. So you have to be a little bit aware of this way of looking at this. And this is the block sphere, I will not detail this. The second system, which is elementary, the second block, I would say, it is as if you are in Lego and you have two blocks, qubit and harmonic oscillator. Harmonic oscillator is the system of infinite dimension, which is of simplest case. So you have in the Hilbert space, okay, you have an Hilbert basis labeled by n, and n starts from 0, not from 1, because 0 corresponds to vacuum, the lowest energy of your system. And on this system, what you need is only A, which is the annihilation operator. With this operator, but take the quantum system of level n to n minus 1 with a square root of n in front of it, you build any other operator on your system with A and A dag. Okay? So you have to master a little bit of this. And in this case, for a harmonic oscillator, what is, in fact, a classical state? A classical state is called a coherent state. A coherent state, it is here you have a different level of energy. So you have 0 photon, 1 photon, 2 photon, and n photon. So you have a ladder like this. Okay? And the energy between the different, in fact, level of this stair are equal, corresponding to a frequency. It is the frequency of your mode. Okay? And in this case, what is a classical pure state? It is something which is, in a certain sense, a Poisson distribution. Okay? Okay? On n. But it is not a purely Poisson distribution. You see, it is a coherent superposition, okay, of different, in fact, photon number state. And we have, in front of this, you have this quantity where alpha is a complex number. Okay? And what you see, the Poisson distribution is just, in fact, the square modulus of this guy. And you obtain a Poisson distribution. Okay? Voilà. So I wish this by this. So this is the two key elements that you have, in fact, to be a little bit aware on that. And the last point, it is this one. It is what is called the Wigner function. The Wigner function, it is, imagine that you do a simulation. You obtain a vector like this, with n is equal to 200. And you want to see what is the state inside this guy. The state, you will see, we will need, in fact, the density operator. So it is a matrix 200 by 200. You want to see a way to look at this matrix, in fact, is to use something that has been imagined by Wigner. It is this guy where P and Q corresponds to the classical position impulsion. Okay? And W is a function which is real. Okay? And it is what is called a quasi-probability. So when you have a classical state on this thing, which is a mixture, statistical mixture, it will be positive. And when you see some negative part in the Wigner function, then it is something which is completely, in fact, a quantum. Okay? Voilà. So to get an idea. Okay. And then, so once you have this thing, Schrödinger evolution, okay, randomness through the measurement of the wave packet, and its collapse, you have entanglement and tensor product for composite system. You need to have classical probability to take into account the fact that your measurement could be not perfect. You make some error rates. It gives you that you project on this eigenspace, but in fact, the true projection is on the other one. So for this, what you need, additionally to this, you need, in fact, what is called here eta. It is a matrix, which is a left stochastic matrix. So it is a matrix, okay? And to represent this guy, 1, 2, and 3, what you need this form here. K of u, depends on the control. It is something like this. And look, it is a sum of, you put the density operator in the middle, you have an operator on the left, density operator, the Hermitian conjugate on the right. And you put, it depends on you, or your control input. Okay. It's the way that you summarize all these things. And so what is called in quantum information, what is called a quantum channel. So this map, K, depending on your control, in fact, it is linear with respect to rho, and it preserves the trace. This is the Schrödinger evolution. The trace means that this M and M dab, you can see them as weight, but non-commutative weight. But the sum of the weight should be 1. It is this. You have sort of kind of partition of identity in this way. So this thing here, K of u, summarize 1, 2, and 3. And you need to add 4 to mix classical and quantum probability, okay, to get, in fact, the input-output relationship. So the input-output relationship tells you, it is in a discrete time. You have a density operator rho at time t. You measure something at time t, and you obtain a new rho at time t plus 1. What you do is that, in fact, you use, in fact, some element of this time times some weight, depending on eta. You take the sum of all on mu. So you have something where you take the sum with respect to I, to y, it is the quantum channel. And you have something that, in fact, you do not preserve probability here. The trace of each of these guys is not 1, but it is less than 1, of course. And this is precisely the trace of detecting y, knowing the quantum state before the measurements and your, in fact, input signal. And you normalized. And here it is the structure of a model of open quantum system in discrete time. You have no other structure. Okay? In a certain sense, it replaces, I will say, a Newton equation for a mechanical system. Or Euler-Lagrange equation with some Rayleigh dissipation and something like this, it is this. Okay. And then, in continuous time, when you look typically in the book of Italian colleague Barcelli and Gregorati, which is a very nice book, but it is highly mathematical. What you obtain, instead of this, you need, in fact, to do this in continuous time. So you need some, in fact, stochasticity. So stochasticity in continuous time, either you are Poisson noise or, okay, or Wiener noise. So in Wiener noise, in this case, so you have dW. Here you have rho. You have a deterministic evolution of rho. You recognize here the Hamiltonian, and here it is correspond to decoherence. And here what you see, you have some noise. And this is the output map. So you say, well, it is more or less like in Kalman filtering. You have noise in the state equation, and you have noise in the output map. But here, the fact that you have a measurement back action is that the noise is exactly the same, which gives you, in fact, what is called the measurement back action. It's the way that you encode the fact that when you detect y, dy, a small increment, okay, what you take dy, you subtract this guy, and you take dw, you put it inside this, and you integrate. It is called a quantum filter. Okay. And how you can write this map, okay, like this, in fact. It is just by doing some Ito computation. What you have, this map is something like this. and you recognize here on the top something which is operator time row time operator and a sum, where in fact you have a measurement appearing. It is like this, and here you have to normalize, and here instead of having probability you have probability density. But it is exactly the same. This thing or this thing, it is exactly the same object, but it is written in another way. From this formula, you see that if rho is positive, it remains positive, and the fact that the trace of rho is 1 always. So you are with a quantum state. What time is it? Yes. Okay. So, and now what about quantum controller? Okay, so you have a structure of a model. Okay? With this, let's go back to Watt regulator. So if you take the Watt regulator, so you have a regulator, and here is the input flow, the steam flow input. So you see you have a coupling, it's a mechanical coupling, okay, like this. And if you write down something which is the simplest model that you can imagine on this system, you recognize here the oscillation of this around a certain frequency, a certain velocity of the steam machine, omega. It is the oscillation of this pendulum in a certain sense. And here you see it is just the coupling of the, in fact, 0 point of the pendulum, okay, with respect, in fact, to this thing. And here in this case, you see the coupling is like this, such that when delta theta decrease, okay, then you increase. This is the conservation of momentum on the things. You increase, in fact, the input force, the force, okay? And when delta theta decrease, okay, you increase, you decrease the things. So it explains the sign. And if you look at the stability of this guy, you obtain a third order system. And it is amazing to see that you need some damping. And if the damping is not enough, the system isn't stable. It's quite amazing, this. So you need to put damping here to stabilize your system here. More or less, it's the same for quantum system. We'll take quantum system here, which will be the red part. It is almost Schrödinger. And we couple it with an Hamiltonian, okay? And from this, and the system, which is your controller, is in blue, and the coupling, in fact, and it has some damping. And damping, it is where it is there. It corresponds to this term in the, in fact, evolution of your system. This is Lindblad term, which is different from H. It is what is called decoherence things. Okay. So if you mimic this, the strategy is quite simple. You have your system, you have your controller. Controller is a quantum system with dissipation, okay? And typically what it is for us, it is a harmonic oscillator, but with damping, which means that the energy which are above the quantum, the zero energy, tends to decrease, okay, with this. So you have this. You have to engineer correctly the interaction such that if you have your system like this, it converges typically to something which is a separable state. You have a density operator for your controller, and you have some projectant. Typically, if you want to prepare some state inside your system and stabilize it, you want that any rho, which is in the tensor product, converge to something on the system, tensor something on the density, on the controller. And you assume that it is pure, this. It is rank 1 projector. Okay. If you do here, if you say, well, my system has noise, has perturbation, and so on, you will assume that the noise, okay, is not too important with respect to what you have here. And at the end, what you obtain by robustness, you still have something converging. If you have initially, in the pure case, in the perfect case, exponential convergence, then you will have some robustness, so you will converge to something which is not exactly what you want, plus some error, but you can imagine that this error is small, okay? If you have, in fact, a convergence time with gamma is equal to 0 is much larger than the decoherence time. It's much smaller than the decoherence time, which is much, much longer. Okay. And the convergence, it is, so from a mathematical point of view, what do you have to do? You have to consider the Lindblad equation, okay, like this. But on the composite system, you are on the tensor product. And you have to look at the property of this, I will say it is something which is a linear, in fact, equation. You say, well, it is linear, but it is an operator. And sometimes, time to time, you are in infinite dimension. So it's not so simple. Okay? And so you have a lot of property of this, but one is the fact that any equation like this is a contraction, whatever H is, or the jump operator L nu R. It is a contraction, but for L1 norm, not L2 norm. It preserves positivity. If rho is positive, it remains always positive. The trace is positive, which means that if you find an Hermitian operator, which is a positive operator, such that, in fact, what is called, it is the adjoint equation, the adjoint of this dynamics. It is typically this one. It is negative, which is the Heisenberg point of view. Okay, it is this. Then this guy, which is a linear function, is a Lyapunov function. It is something in a certain sense that mimics, you know, what we know on systems which are invariant with respect to the positive quadrant. But here it is for matrices. So it is in the non-commutative case. Okay? So, and now let's go, in fact, to what we called autonomous quantum error correction for bosonic code. So first, what is the problem, in fact, of correcting error for, in fact, for a qubit? In fact, for a qubit, you have two, it is what has proved sure, you have two, in fact, fundamental error. You have a bit flip, okay, which means that 0 becomes 1 and 1 becomes 0, or the ground state becomes excited state, or excited state becomes ground state, okay, it is classical error for a classical computer, but you have also a phase flip. A phase flip means you that 0 remains 0, but 1 becomes minus 1. Okay? So it is, in a certain sense, in the space where 0 is horizontal and 1 is vertical, it is a symmetry with respect to the vertical axis. Okay? And if you have, and this is what Shor proved, is that if you can correct these two kind of error by redundancy, okay, you can, in fact, achieve a much better, in fact, logical qubit than the physical qubit. But because of these two kind of errors, you need redundancy along two directions, which means that this is the physical qubit with some error, bit flip, phase flip, and bit flip, and you need here a certain redundancy for the bit flip, and here a certain redundancy for a phase flip. Okay? And if you look at typical size, if you take something which is 10, redundancy of 10, because your physical qubit has not a very good quality, you see, to encode the logical qubit, you need 100 physical qubits. You can imagine if you want to have many logical qubits, the overhead is quite large. Okay. So, it is clear from this thing that I have one qubit, and here I am on the tensor product, which means I have on the Hilbert space of this guy, if it is 10 by 10, is 2 power 100. Okay? It's important to realize this. You have almost 2 power 100, it is an infinite dimensional space. So, and it is clear that you can more or less do the same thing, but with an harmonic oscillator, where you have already an infinite dimensional space. So what you want to do is you have to encode, in fact, your qubit in a much larger Hilbert space, such that, in fact, you achieve convergence to, in fact, the code space where, in fact, it is protected from the noise. And the noise, you have a very strong assumption of the noise in this thing. I assume that the noise, the bit fit and phase flip of each physical qubit is independent of the other physical qubit. It is independent local noise. In this case, you can imagine this is the Wigner function. So this corresponds in a certain sense of the state of your harmonic oscillator. And here you can imagine that the noise in this case, what it is something which is small deformation of W, the Wigner function, which means it is a differential operator. It is something which is local in the phase space. Here you have Q, here you have P, and you are in the phase space. Okay. And here it is the definition. And one point is that this transformation is well used in signal processing. It is the Wignerville transformation, in fact, of a signal, this thing. So if you want to do this with MATLAB, you have all the things to do to compute this. So with a signal processing toolbox. Okay. So this is the local noise assumption. I will not enter in detail. And what's going on, what we are trying to do is to encode in the group, this is this thing here. We encode, in fact, the logical qubit. It is called bosonic code, in fact. So I am in an infinite dimensional space. I want to encode my information in a two-dimensional space, which is inside this. What are the basic elements of this two-dimensional space? But you take classical state, because classical states are robust to decoherence. And what are the classical states for a harmonic oscillator? It is a coherent state. But you take a coherent state, typically, of amplitude alpha here, okay, in the phase space. Alpha, it is Q plus E P, P. So it is the position. And I take, in fact, the vector space by the coherent state of amplitude alpha and minus alpha. And it is called, and you take alpha plus minus alpha, it is called a phase Schrödinger cat, which is it is a coherent superposition of two states, okay, that have almost no overlap. And you can see this here. This is the coherent state, the Wigner function of the coherent state with, in fact, in position Q. So if you take the, I will say, the classical analog of this, it will be a Dirac at exactly, okay, 2 and 0. Okay? So it is a Dirac where, in fact, the velocity is 0, okay, and the position is 2. Your particle is there. If you take the other one, it is exactly the same Dirac, but with position minus 2, velocity 0. But you are in a quantum state, so you know by the uncertainty principle, but it is not a pure Dirac, it is a Gaussian. So you replace the Dirac by a Gaussian, and if the standard deviation is very close, it is as if you have a Dirac. But the problem is this. So it is the Wigner function of this guy. This guy, if you have some engineering, some dissipation that tends to converge to these things, it is okay. If you put some diffusion, there is no problem here. The Gaussian will be a little bit larger, but if the diffusion process is much smaller than the convergence process, you will have something which is essentially concentrated here and positive. It is exactly the same thing for the other side, so there is no problem. I cannot, if I am here, with my thing, I cannot jump to the other one. The probability is very low. So which means that the bit flip error, you almost suppress it. But if you take, instead of this, you take the coherent superposition. It is this guy plus minus 2 square of this guy. And it is, you have to understand this very important. It is important to understand this. If I take rho, which is in fact the plus state, plus, what it is? I develop, okay? It is 2 pi, almost over 2, plus minus 2 pi over 2, but you have plus 1 over 2, and here you have what is called the coherence. Okay? You have the rectangular things. Okay? And these things, so this guy and this guy, it is, you take the linear function, which is a linear function of rho, it is this one and this one. So you have probability 1/2 here, but you have a coherence. And the coherence, it is exactly what is, it is exactly what is here. It is the fringe. So typical physicists say that it is a cat with 2 legs here, and here it is the moustache of the cat. And imagine that you have diffusion. Diffusion will kill you this thing, because the positive fringe are very close to the negative one. And if you take a cat of large amplitude, okay, you put, instead of 2, you put 4, for example, you will see that the fringe become, in fact, narrow and narrow, but they are very close one to each other. So you are not robust. And if you have a bit flip, a phase flip, it is this guy remains okay, but this guy get a minus. So you have this guy becomes this guy, and you see the fringe in the middle. So the positive fringe for plus here, it is positive and negative, and here it is just a vertical shift, okay, of the fringe. Okay, you see. So, which means that this system, okay, it is very difficult to observe and to, in fact, to have in a natural system, but such kind of state, okay? So, and how to do this? What time is it? So I don't want to bother you. Yes. What you do, I will not do it. I will do nothing. It is something, so we are looking at what is called the support to do this. It is in the group, so it is with a recent experiment. So here it is the harmonic oscillator. In electrical engineering, it is an LC circuit of very good quality. So the quality is typically here, it is something where it is around gigahertz, okay? So it is microwave engineering, okay? And here what you see, you have something where you have capacity coupling. This is your controller with typically the drive here, corresponding to external flux, so you have flux loop here. And here you have linear inductance, and this thing, it is what is called Josephson junction. So it is a nonlinear inductor. So you know that the energy of an inductor, it is the flux square over 2L. For a Josephson junction, the energy, it is something which is cosinus phi over the quantum of flux, phi 0. So it is a nonlinear phase. Okay? It is minus cosinus. Okay? So, and it is, so we use this nonlinearity and some coupling here, such that I do not have the trick. So here I have dissipation, okay, in this case. And here, if you write down now in fact, so the last point to be aware is that this oscillator is gigahertz. This one also is some gigahertz, weakly coupled. Okay, but it has some damping. If you couple them through, in fact, a small capacitance here, you have two oscillators, in fact, energy coupling with an Hamiltonian, and you put some dissipation on one oscillator. You know that the overall system will converge to something because it evacuates energy. And you know that at the end, you have two oscillators which are conservatively coupled with some damping on one oscillator, or if you have two wave equations which are coupled by something which is, in fact, we preserve energy, then you put some damping on the one wave equation, you know that your system relaxes to 0. And here, more or less, it's the same thing, but the trick is that here it is the damping, in fact, of the low Q oscillator of my controller, but here it is the coupling. And the coupling is very important. It is, what is B? B is the fact that you destroy, okay, one quantum in vibration in the in my controller. But in front of it, I have ADAG2. So I need two photons inside my system, okay, that get outside my system, that becomes one photon that are destroyed, in fact, by the thing. So here I lose one photon, and here I gain two photons. Here I gain two photons, and I lose one photon. And this is of this two photon, one photon, in fact, coupling. But in fact, here, you don't see, in fact, the phase of your system. So in a certain sense, if you try to see a classical analog of this, so if you write down the classical analog of this, it is as if, so it is a nice classical mechanical system. So you have a pendulum system like this, okay? And you assume that the suspension point, okay, is moving like this, okay? And you put some damper here. And you know, and what you see, what the environment see, is in fact the velocity inside the damper. Because of the symmetry, you cannot see if theta, the angle, is positive or negative. If you look at the observability from, in fact, the velocity in the damper to theta, you have two branches in the observable system. And you don't know in which branch you are, which means that it is as if you are a sort of interferometer with, in fact, Young slide, okay? You can pass through one or to the other one, and you do not have information in which slide the photon has passed when you see the detection on the wall behind this. So it is something which is similar. So we can see this, and at the end, you can prove that you control to this, and you have a Laplace function here. When you assume that the damping here is large with respect to the coupling, you can use what is called singular perturbation. Okay, go back to the famous work of Petar Kokotovic, I would say. I learned singular perturbation from Petar Kokotovic. Okay, all this thing. Okay, and you can just concentrate on the slow system, and the slow system is this, with this dissipation, and you can prove that you converge to the code space. Okay. Right. And then you can do the error analysis, and you see when you take alpha as a parameter in your system, when you increase alpha, which is the size of the cat, you see that the bit flip time increased exponentially, whereas the phase flip time decreased, in fact, in a polynomial way. So you gain. You have something where you kill almost, in fact, the bit flip, and you have only one error to correct. Which, if you consider this scheme where you have only one error, what you can use is for each qubit here you use a cat state, a cat qubit, and you just have a redundancy of one, okay, and you decrease, in fact, the physical overhead. So, it is not my idea, of course. This is an idea of Mazir Meraimi and Zaki Lektas with Michel de Moret, where they were at IDL. When Mazir Meraimi and Zaki Lektas, it is two of my former students. So I have a huge chance to have very good students. Okay, it is a key issue. You know, to have very good students is a very key issue. Okay. So they have this idea, and it's go on the go. Okay, so you understand on this thing that you preserve bit flip, but phase flip, it is exchange plus and minus. You cannot preserve this. And in the group, we are working on the next generation, of course, on this. It is called grid state or GKP qubit. It is an idea of, in fact, a group around Presqu'île at Caltech more than 20 years ago. Okay, alors GKP, it is from Kottesman, Kitaev, and Presqu'île. Okay, you have recent experiment, in particular one of Philippe Champagne, which is in the group, was doing this postdoc at Yale. And the trick is this. You know that the Fourier transform of a Dirac-Combe is a Dirac-Combe. Okay? If the Dirac-Combe is very thin, the Fourier transform, it will Dirac-Combe very loose. Okay? So what you have this. So you take a Dirac-Combe of period t, in the P variable, so Q is the Q variable, P variable, it is a Dirac period 2 pi over 2. So, and then what you use T is equal to, in fact, 2 square root of pi. And you assume that, in fact, you will encode the system in. So, you have a periodicity of 2 the square root of pi, okay, in this, okay, and you have, so the spike like this, and you have a spike at odd position, at, yes, even position here and odd position, in the Q representation. But in the P representation, it is exactly the reverse. Okay. The odd position becomes, the even position becomes odd, and the odd position becomes, in fact, like this, with a minus 1. And plus and 1, it is something like this. So with this kind of state, it is Dirac. So it is not, in fact, possible to prepare them because it is infinite energy. Okay. But what you can do is you can regularize by convolution with respect to a Gaussian, a small Gaussian. It is this operator here, which is a small Gaussian. Okay. Here it is this. And then what you can do is to have this kind of state, which is a finite energy JKP state. It is exactly what you see. It is in the Q representation. You have your, in fact, small Gaussian centered at 2 odd position with respect to square root of pi. Okay, here. And you take an envelope which is of a size 1 over epsilon. So the concentration is epsilon and the envelope is 1 over epsilon. Okay? If you do, for this thing, in fact, the Fourier transform. The Fourier transform in the phase place is just a pi over 2 rotation. So you take this picture, which is the Wigner function of this guy, and you obtain this. You see, it's just a rotation. And assume that you have on your system some local error, which means that assume that you tend to engineer, in fact, dissipation, but you converge to this, and assume that you put some small diffusion, so a small Laplacian. Since, in fact, the positive spike in the Wigner function and the negative one are separated by 0, you have some margin. And if you decrease epsilon, the concentration, okay, the distance between plus and minus tends not to decrease. It tends almost to increase up to, in fact, the size, in fact, of periodicity, square root of pi. So because of that, if I put, you see, some dissipation on 0, I will have something which is look more or less like 0. If I put the same dissipation on plus, I obtain exactly the same thing. And if I do this for 1, it is just a shift. And if I do this for minus, it is the same. So in this case, bit flip and phase flip, you can reduce them. Okay? Very rapidly, in fact. And so I have discussed this, so we have investigated. It is up to now something which is, in fact, formal results. So we have the Lindblad equation with dissipator, and we prove, it is standard things, that we converge exponentially to this, and here it is the state where you converge. It is something just, can we imagine some dissipator such that we converge to this? Yes. So it was published in the CDC. We can do something which is more realistic, because when you look at this operator here, it is as if you have exponential of epsilon p. So it's not so nice. Exponential, the p, it is the I d over dq. So it is exponential of I epsilon d over dq. So if you look at this operator, it's not nice operator. Okay, it's not a delay, because it is as if you have a delay, but with a complex delay. Imaginary delay. It is exactly this operator. So it is not nice. But if you take typically the first order approximation with respect to epsilon, then you can prove, in fact, that inside the code space, you have in fact dissipation, okay, which is exponentially slow with this. And it is based on typically something which is called beaten Laplacian and so it was in the IFAC World Congress in Yokohama 2 years ago. Okay. And you say, well, and in this paper, we propose, I will say, a quantum superconducting circuit, which is not completely realistic. But it is very difficult to do this. Just to see, so here it is your storage oscillator, and here it is your, in fact, dissipation. Here you put a resistance, okay? Dissipation, it is a resistance. So it is your controller, and here it is the coupling between the two. And we use external flux, okay, on flux loop here. And the flux here that you put, it is something which is from time to time some frequency comb in time. So it is not so simple to realize this kind of thing. And with this, we can engineer this kind of dissipator here, which are in fact such that if in fact we are close to this, we assume, we guess, that we will protect in an exponential way either the bit flip or the phase flip. So in this case, you can imagine that you can have some, in fact, physical qubit of very high quality. In this. But it is, I will say, work in progress, of course. So, to conclude, I think it's okay. To conclude, here is my big scheme, I will say. You combine two. So it is like for remote control, when you take typically some, what is this called? UAV, so which means the people, the drone who are moving. So you have some local controller and you have remote controller. Here in the certain case, the local controller is quantum controller to control short time scale and to stabilize your system. And then you can imagine something, because you have a feedback delay here, some quantum measurements and of course some control input to finish the job typically, to identify some small frequency shift or something where some error that are very weak and you can compensate something like this. Okay? And the problem is in fact is to decompose the control scheme of your system by what will be quantum and what will be classical in this case. Okay? And it is not so simple, of course, and it depends on what kind of physical resource you have. Here you can do almost everything, okay, with classical computers, except the fact that the time scale, it is not picoseconds. Okay? You need some time to do the computation. So you are limited by, in fact, the control electronic here, FPGA. Okay, you are limited by this, and the delay. And here you are limited by, in fact, your quantum building blocks. Okay, this way. So it is something you have to make always trade-off between what you want to have and what you can realize in the lab. Okay, and of course, I am not alone for that. Most of what I present is idea of the group. Okay, and the leader of the group now it is Nazer Miraimi here, and here is Philippe Campagne working on GKP. And here you can recognize me. I am protected by 20 years of gap between the oldest guy except me in the group. So it's well, thank you.